Okay, so maybe we get started for the folks online. So welcome to our Frontiers of Condensed Matter Physics series. And today we have the pleasure of welcoming Santi Blanco-Canosa from DIPC to give us a talk on electronic structure and lattice dynamics in Kagome metal. Santi is an expert in X-ray scattering, ARPES measurement. He has really contributed to a lot for different kinds of Kagome materials, TMT materials, cuprates, using a variety of techniques, experimental techniques, synchrotrons, and so on and so forth. So I guess we're looking forward to hearing your results on Kagome metals.
Thank you, Mingy. Thank you, everyone, for inviting me here. It's actually my first time here at the Rice University in Houston. And yeah, I'm particularly happy about the weather since I come from Chicago and it was a bit cold there. So I'm talking about electronic structure and lattice dynamics in Kagome metals, which is one of the research directions I am working on now, besides transition metal dechalcogenides. And I come from the Donostia International Physics Center, which is located in the north of Spain in San Sebastian, which is very close actually to France. So the work, this is the line of the talk. I will give a brief introduction about Kagome metals, about electronic structure and lattice instabilities, in particular in charge density waves we encounter in these materials. And then I will show you some results, scandium 6, vanadium 6, scandium vanadium 66, iron germanium. I'm not talking about the ytterbium cobalt 6, germanium 6. I just removed the slides there because otherwise it will be too long. But I would like eventually to mention something about the 166 lutetium iron germanium. So why Kagome metals? Why these compounds are so interesting right now? So these are Kagome metals are just a frustrated, geometrically frustrated triangular lattice. Contains the unit cell is composed of a hexagonal Kagome layer, triangular Kagome layer, which has a transition metal atom with a trigonal tin or germanium on top of the voids of the hexagons, plus a honeycomb layer separating this Kagome layer. So here I show the structure of the iron germanium, 1,1, iron 1, germanium 1. This is the simplest Kagome metal we can find. It has the same structure as the iron tin, and we see that the Kagome layer is formed by the iron transition metal ion in this plane separated by the honeycomb germanium layer. So one can actually understand the whole family of transition, the Kagome metals, by just piling up these Kagome layers along the z-axis, stacking them along the z directions. So for the 1,1 material, we have the simplest unit cell with one Kagome layer separated by, as I said before, by the hexagonal honeycomb layer. But then if we increase the ratio of the transition metal with respect to X, where X is germanium or tin, we can actually form the whole family of Kagome materials ranging from the 166, which essentially is doubling the 1,1 iron germanium or iron tin, and then stacking or interleaving several honeycomb layers. So from the electronic point of view, these materials are becoming very hot topic, and the reason for that is that they host flat bands and Van Hoff singularities. Flat bands are in the reciprocal space in the Johnson, and Van Hoff singularities at the endpoint and the dark crossings at the K point. So this geometrical frustrated lattice, together with these electronic features in the band structure, are actually very important to study correlated phenomena, like for instance charge density waves, static magnetism, or even superconductivity. So one way to understand this band structure, which actually is very complex, we have these Kagome materials are multi-band systems, multi-orbital systems with a lot of bands crossing the Fermi level. So one way to easily understand that is starting from a honeycomb lattice. Honeycomb lattice has two sides per unit cells, which I show here. And the electronic structure of the electronic spectrum, the energy spectrum of this honeycomb lattice actually is characterized by a Van Hoff singularity at the endpoint, the two Van Hoff singularities at the endpoint that they cross linearly at the K point. So if now we connect the middle points of this honeycomb lattice and start and form a line graph and start to populate the triangles or the corners of this triangle, we end up with a tripartite lattice, which inherits the Van Hoff singularities at the M point and the Dirac crossing at the K point from the honeycomb structure, plus one flat band, or actually the number of flat bands depends on the number of sides in the bipartite or tripartite lattice. But we inherited the honeycomb energy spectrum plus a flat band. This is the energy spectrum of this is actually derived from the S orbital type binding model, which is a very simplified model. In reality, as I showed before, the electron band structure is much complicated, but we can easily understand that this Van Hoff singularities and Dirac crossings starting from this type binding S model, which only considers hopping from the nearest neighbor. Once we put hoppings to the next nearest neighbor, the bands are no longer flat. But anyway, what we can do, and we can play around with the Kagome materials, is to put the chemical potential, tune the chemical potential through the Van Hoff singularities, Dirac crossings, and flat bands. So, for instance, if the chemical potential falls into the Dirac crossing and the spin-orbit coupling opens the gap, we can end up with topological protected edge states. If you put the chemical potential exactly at the flat band, we have this flat band arises from the distracted interference of the electronic wave function. So this flat band at the Fermi level can actually lead us to exotic magnetism or even superconductivity. There are predictions of high Tc superconductivity when the flat band falls at the Fermi level. In any case, what we are interested somehow I see here this here. What we are interested in is mostly when the flat band, when the chemical potential falls at the Van Hoff singularity, 512 filling, 5 and 312 filling, because here we actually have a high density of states. The electronic spectrum, the energy spectrum develops a logarithmic dependence of the density of states, which drives the formation of the charge density waves and other broken symmetry orders. In particular, this high density of states, which can be driven, appear as can drive the nesting between Van Hoff singularities, can promote electronic instabilities, like as I mentioned before, the charge density waves. And these charge density waves in the Kagome materials, it actually can be divided in three different groups, three different types, depending on the eigen displacement of the atoms that drive the imaginary modes. So we characterize these charge-ordered materials, the charge-ordered Kagome metals in three types. So type 1, the leading instabilities along the gamma A direction and involves in plane displacements of the transition metal atom. As type 2 presents a nearly flat band, flat imaginary mode along the gamma MK direction and implies that the eigenvector of this atomic displacement is an in-phase vibration of the out-of-plane in-phase vibration of the transition metal plus trigonal atom. And the type 3 charge density waves are actually driven by the condensation of a out-of-phase, out-of-plane vibration of the trigonal tin or trigonal germanium atoms in the unit cell. So in this talk, I will mostly focus on the type 3 charge density waves, which indeed, for the case of scandium vanadium 16-6, happens to have the same electronic structure of the 135 cesium vanadium 305. This is the first Kagome metal, as far as I know, reported so far. It has a charge density wave around 94 Kelvin, with a peak in the specific heat. I mean, there are a lot of reports and a lot of controversy about the low temperature phase of the charge order. It's a multi-Q charge density wave with propagation vectors connecting the M and L points of the Brillouin. In any case, what we know so far, and it is for sure, it is quite stable and quite solid, is that the charge order is driven by the primary order parameter in this compound is actually the L point and not the M. I reported that there is, there are reports now that the charge density wave is driven by the condensation of a soft mode, which was experimentally observed. Papers are at in archive. And also this compound shows superconductivity. There is also no solid establishment about the origin of the superconducting order. It's also highly discussed the possibility of the chiral charge density waves and so on and so forth. In any case, I'm not talking about this guy. This was the first paper, the first compound which brought this hot topic to where we are right now. What I'm trying to do in my job, in my work, is essentially studying the origin and the mechanism for the stabilization of the charge order in this Kagome method. So for that, I mostly use diffuse scattering and elastic X-ray scattering. Diffuse scattering is nothing else than normal diffraction, but instead of focusing on long-range order, like measuring Bragg peaks, we focus on short-range correlations that appear as a precursors or a pre-transitional fluctuations of a charge order phase transition at lower temperature. And on the other hand, this technique allows us to distinguish the primary order parameters in these multiple Q charge order materials. We know that diffuse scattering may appear due to the deviation from a perfect crystal, like defects, vacancies, and so on and so forth. In our case, we assume that our samples are not really perfect, because in reality there are no perfect samples, but the disorder and the number of the defects and the vacancies of our samples are essentially minimum. We don't want to work with or deal with, let's say, bad samples. Diffuse scattering is an energy integrated experiment. So we see some signals, some blob of intensity in the diffraction pattern. It actually may come from the elastic process or from some inelastic phonon mediated origin. For that, we take the sample to inelastic X-ray scattering beam line, usually at the SRF, Japan, or in Chicago. And the idea is just to separate or resolve the energy spectrum in the scattering experiment. So if this diffuse scattering comes from phonons, we will see some anomalies in the phonon spectrum, or if it comes from some static elastic signal, then it shows up as a zero energy loss. So the key point in this inelastic X-ray scattering experiment is just that we will see a phonon. So a photon will scatter off a phonon if the propagation of the eigenvector of this phonon is parallel to the momentum transfer in the crystal. So with that selection rule, we can actually move from transversal to longitudinal modes, and we can selectively move measuring in different positions of the Bjornson, and we can selectively prove different phonons of the crystal. So the first type of material I'm talking about is scandium 6 vanadium 6. As I said before, it's a type 3 charge order material. This is essentially, the diffuse scattering looks something like this. It's just to make the story short, with this HK 6.5 plane. It has some triangular shaped diffuse signal, which increases once we cool down. And the other example is the iron germanium, which at high temperature has the diffuse scattering, so some hexagonal shaped charge precursors which condense the M, L, and A point of the Bjornson. We first start with the scandium 6 vanadium 6. It contains two Kagome layers made of vanadium and trigonal germaniums. Sorry, trigonal tins. Blue and the blue atoms are trigonal tin. The green are vanadium. So the blue trigonal tin are not aligned in the Kagome layer. Actually, they are a bit slightly above and below the Kagome plane. And this is a consequence of the small size of the scandium atom, which is located at the same height of the honeycomb tin layer. So the compound has a charge density wave with propagation vector 1/3, 1/3, 1/3, below 95 and 100 Kelvin. There are anomalies in transport, like resistivity and magnetization, and also a small peak in the specific heat. So this 1/3, 1/3, 1/3 peak is not a high symmetry point in the Bjornson. The 1/3, 1/3, 1/2 is the H point, 1/3, 1/3, 1/3 is between K and H. In principle, we don't expect anything electronically there. So it has the same feeling as the 135 cesium vanadium. As I said, the temperature, the charge order transition is around 95 Kelvin, which oscillates between 95, 92, and 100, depending on the quality of the sample. And the first we notice is that the charge order is actually a first order in character. So it has a small hysteresis, but as we measure in the resonant diffraction, it's actually very sharp, around 95, 98 Kelvin. So we take the sample and we put it in the diffuse scattering, and already at 300 Kelvin, we see some diffuse signal in the HH plane, like streaks of intensity at half integer values of L. Once we cool down, this diffuse scattering starts to increase in temperature until we reach the transition temperature of 95 Kelvin, and then the diffuse signal actually suppressed, and the super lattice peak at L1/3 appeared. So we can actually see, if we look at the diffuse signal along the L direction, we actually see how the intensity increases with L, which essentially tells us that we are dealing with the diffuse scattering coming from the condensation of a soft mode. If it were related with disorder or occupational substitutional disorder, the diffuse scattering should decrease with momentum. On the other hand, we can also distinguish how the diffuse signal changes, the intensity changes from high, low, high, low, high, low. And this is essentially telling us that the soft mode is a consequence of the out-of-phase vibration of some atom which displaces along the Z direction. I will show you later from the DFT calculations that this corresponds to the trigonal team, just slightly above and below the Kagome plane. So if we look then at the HK plane 6.5, we actually see that the diffuse scattering has this triangular shape. So essentially, we don't see diffuse scattering at the K point or A point or M points, which are the high symmetry points in this other high symmetry points in the reciprocal space. But we see diffuse signal, a precursor of the charge order at L1/2. I have to recall that the charge order happens at the L1/3. So 1/3 and 1/2 are two different propagation, two different wave vectors in the bridge answer. So the L1/2 is actually the primary order parameter that drives the phase transition at of this 166 scandium vanadium tin. So we can actually parse in detail the diffuse signal. We make cuts along the Z direction and feed it to a Lorentzian line. We see how the intensity increases and sharply drops. And most importantly, the out-of-plane correlation length follows an order parameter with a critical exponent close to 0.5 along the Z-axis, which essentially tells us that the phase transition might be of a mean field-like, right? But as I said before, the diffuse scattering is energy integrated experiment. All the energy comes to the detector. If we want to resolve what part of this diffuse signal is actually elastic and what comes from inelastic, as inferring from the momentum dependence of the diffuse signal, we go to inelastic X-ray scattering, we put the sample in the beam, and we can record the inelastic spectrum. At high temperature, this brown scan, we see a Stokes and anti-Stokes branch, low energy branch, low energy phonons with more or less 4 to 5 millielectron volts at high temperature. And then when we cool down, we actually can track the softening of this L1/2 mode towards zero energy. If we plot the temperature, the momentum dependence of this 1/3, 6/2 phonon, we actually see that the phonon is not flat. There is a small, actually broad softening already visible at room temperature due to perhaps already substantial electron-phonon interaction of affinity 300 Kelvin. If then we cool down, we actually the L1/2, and we track the momentum dependence, we clearly see how the phonon softens at the 1/3, 1/2 propagation vector. So the phonon, from our data, we see that it actually collapses. It's a soft mode with a freezes down to a long range charge density with long range charge order. And on the other hand, the fact that this sharp, this broadening is broad in momentum space indirectly tells us that we are mostly dealing with a momentum-dependent electron-phonon interaction and not with nesting. We can further track the temperature dependence of the soft mode, and again, we see how it follows an in-field behavior with very linear temperature dependence from room temperature down to the charge order transition.
I have a question. And the stack and anti-stack branches means the absorption and
emission of the phonon.
Okay, so if you cool down, I think one of the branches will not change because always absorb the one branch is absorb the energy, one branch is emit the energy. Okay. One branch is generate a photon, another is also a phonon.
Yeah, that's an harmonic behavior, and the phonon has to harden.
Yeah,
but
if
now
you
the softens because of the soft mode. That's the reason to I mean, if there is a soft mode, it has to soft.
Okay.
According to a phase transition, right?
Okay.
I mean, the normal behavior is that the phonon hardens. Yeah, so as you recall, well, we actually can plot the momentum and temperature dependence of the line with broadening, and the damping ratio. Actually, see how the phonon approaches to a critical overdamp of the critically damped value, which is characteristic of it tells us about the frozen of a soft mode close to a phase transition. But as you recall, the charge order phase transition happens at L1/3, not L1/2. So then if we track the temperature dependence of the L1/3 peak, the phonon Stokes and anti-Stokes, instead of hardening, which one would expect if there is no, well, actually, if we are dealing with the phase transition driven by phonons, the phonon actually softens. The point is that the phonon does not collapse at 1/3. So we have, I mean, the phonon size, I mean, the phonon broadens in a broad region of momentum space, but does not collapse. It actually remains with a finite energy at the critical temperature. But in any case, if we track the temperature momentum dependence of the line width, it tells us about the lifetime of this mode. It actually goes to an overdamp critical regime. The thing is, if we measure, here I showed, if we measure the temperature dependence, not only of the the phonons related with the charge order, phonons related with the propagation vector of the precursor of the charge density wave, but the phonons at the high symmetry points like A and L points, we clearly see how all the phonons soft with temperature. So essentially what we are dealing here is not with a soft mode. It's actually a complete soft plane of phonons, which only collapse at the at the H point of the Johnson, at the 1/3, 1/2 critical wave vector. And this is indeed consistent with theoretical calculations that predict a nearly flat mode in the ALH plane with the minimum energy at the H point. We can put a bit of theory here, a bit of calculations by the group of Andrei Berneric. We identified this soft mode as an out-of-plane vibration of the trigonal tin. Here I showed in this sketch the unit cell of scandium vanadium 16.6, highlighting the Kagome plane with the tin moving up and down along the z-axis. So this is like a Pyrus chain where the trigonal tins move out of phase along the z direction. So this mode actually at high temperature, and for high temperature I mean electronic temperature like several thousands of Kelvin, is nearly flat. It's a flat mode, but when we switch on the correlations, electron correlations, we see it's just a way to switch on the electron-phonon interaction, we actually see how the phonon becomes negative and imaginary at the H point. Still, if we have electron-phonon interaction, we do not only need a momentum dependence electron-phonon interaction, but we also need electrons to interact with phonons, right? So if we look at the electronic susceptibility, we actually do not find any maximum, any peak at the propagation vector of the charge order, not even the real, not even real imaginary part of the electronic susceptibility, which is some kind of weird. But if we orbitally resolve the electronic susceptibility, and we just plot the real part of it, here I plot the real part of electronic susceptibility, which comes from the PC orbitals of tin, we actually can see how the electronic susceptibility peaks at the H point of the Johnson. So essentially what we are dealing here is just with the momentum dependence electron-phonon interaction, where the out-of-plane vibration of the trigonal tin couples to the PC orbitals of tin. So this is still we need to understand why the phase transition is first order. Turns out that the low temperature phase, the symmetry of the low temperature phase allows for cubic terms in the free energy expansion. So the coupling or the competition between, these cubic terms actually allow for the competition between the 1/2 and 1/3 propagation vectors in wave vectors of a charge order. And this competition drives the first order phase transition. There is also another mechanism which I would like to highlight. I eventually removed the slide, but I was talking to Stephen before. It's based on a disorder. We are dealing here with a triangular lattice where we have sides, 3 sides. And so the way to see it is the chains of atoms are in the Z direction. So we have 3 chains of atoms along the Z axis. And in a triangular lattice, this out-of-plane vibration drives kind of a trimedization, which in a high temperature phase is highly frustrating. So the charge order, according to the Stephen Alvarado's model, which I kind of like and I agree, is the charge order, the first order phase transition is considered or is seen as an order disorder transition. Still, this is just a heuristic model. We need microscopics, and the trigger of this order disorder transition is actually the momentum dependence electron-phonon interaction. In any case, this order disorder transition allows me to move forward and to the next case, iron medium. Unlike the 135 cesium vanadium 3 antimony 5 and scandium vanadium 16.6, iron germanium is magnetic. Okay, it is the simplest Kagome unit cell one can find. Is one layer of Kagome, iron germanium Kagome layer separated by honeycomb germanium. It is antiferromagnetic with a transition temperature around 400 Kelvin. And below 100 Kelvin, it has a charge density wave transition to a 2x2x2 lattice periodicity. It was reported actually here in this group, the charge order. Correct me if I am mistaken, this is Newton's coupling. This is, yeah. So this here we can see how a high temperature has some powder rings and a low temperature, new peaks appear in a low temperature phase. So the charge density wave has indeed 3 propagation vectors which coexist. At low temperature, there are 3 wave vectors connecting the A, M, and L points of the Johnson. Is that correct? Yeah. So there is actually a controversy about the origin of this charge order transition. There are, it's actually a complex problem because first the DFT calculations do not show any soft mode in the spectrum. Then if one measures the group of Hu-Miao, measure the temperature dependence of the out-of-plane vibration, which I think it is the trigonal germanium atom, sees a strong broadening and which renormalizes below the phase transition. And in order to get this broadening of the peak, they actually introduce correlations in the DFT calculations, and they actually see how the phonon gets soft. The phonon, what is real, and we are actually very confident about that, and I think all the communities supports that, is that there is a dimerization of the trigonal germaniums at low temperature. So the trigonal atoms, just these two blue guys below the phase transition, approach one to each other, which is a consequence of the antiferromagnetic transition. The question is why the antiferromagnetic transition happens at 400 Kelvin and the charge density wave at 70 Kelvin. So we measured the sample. We actually found that the charge order, the three propagation vectors of the charge order, with 1/2, 1/2, 0, 1/2, 1/2, 1/2, and 0, 0, 1/2. One thing we found is actually that the temperature dependence is continuous, it's not discontinuous. So we didn't find a sharp first order transition, which now I try to believe it is a consequence of the growth. Right, so we know that many people are working now on the annealing conditions just to play around with these charge orders. Some people get more first order, some people more second order. The as-grown crystals we got from Dresden show a continuous second order like phase transition. And we can actually track the temperature dependence of the lattice parameters. You see how they face the charge order at 98 Kelvin, 95 Kelvin, and some kink in the A around 115, 120 Kelvin. So we'll come later to this T star temperature when analyzing the diffuse scattering. If we look at the electronic band structure, I mean, we see how complex this is. Here I highlighted the PC orbital of trigonal germanium, this electron pocket around gamma, which at low temperature, I mean, this is the calculations of the band structure of the germanium charge density of an antiferromagnetic transition. So it's actually very complex. This is something which, I mean, if you want to match something here, I mean, this is very difficult, right? So the point is the band structure, both in the normal state and the charge density wave antiferromagnetic state, presented flat bands above and below the Fermi level, and one-hole singularities and Dirac crossings at the M and K points. Again, which is also a common feature in these Kagome materials, that we encounter surface states, surface bands due to different surface terminations. So we mix and merge this charge density wave antiferromagnetic and different surface terminations. We end up with a complete mess of band structure. So we put the sample on the ARPES beam. We can actually see the hexagonal Fermi surface typical of a Kagome material with pockets at the K point and some low intensity in the gamma prime due to the position due to the matrix elements in ARPES. But then, if we compare the bulk band structure obtained from the low temperature phase, which we actually resolve with the experiment, we can see some bands which actually match, like for instance, these bands here, which cross at the K point, correspond to these ones, Dirac crossing one. Then there is this band at gamma, which is this one, right? So I would like, and the other bands at the which we cannot match, it actually comes from the germanium 2 termination, the honeycomb termination. So we mix the bulk band structure plus the surface bands from the DFT and compare with the experiment, we can actually match this flat band here with the surface band in the germanium 2 termination. So we put all together. I wouldn't say that we could have a perfect match because the material at low temperature is composed of ordered dimers and ordered and disordered dimers, as I will show before. But we can actually describe the electronic band structure pretty well without assuming any bandwidth renormalization in the spectrum, right? So the message I want to convey here is that the electronic band structure of the iron germanium is not as much correlated as it was previously assumed. We can actually take the charge density wave antiferromagnetic phase plus germanium surface termination, and we can match the flat band at gamma, which is a surface band, and Dirac and velocities crossing the Dirac band. In any case, I would agree with any of you if you think that this complete huge number of bands, many bands can match to any in the spectrum. But at least we get a better match between ARPES and DFT. So since we don't see such much correlations in the ARPES and DFT calculations, we actually want to understand what's the origin of the charge density wave in the iron germanium. So we do the same trick. We put the sample in diffuse scattering, and at room temperature in the HK2 plane, which corresponds to the M point, or maps the MK gamma MK plane. At high temperature, we see a hexagonal diffuse scattering, which once we start to cool down, the diffuse scattering start to condense at the endpoints, right? And below the transition temperature, which we have here the charge order transition. The same if we plot at the L3, we have this the diffuse hexagonal ring, and below 125, 120 Kelvin, the diffuse scattering condenses into a long-range charge order. So this long-range charge order, this hexagonal diffuse scattering actually is a hallmark of a strong frustration, geometrical frustration. It's actually widely reported in magnetic materials in hexagonal lattices, which are magnetic, antiferromagnetic hexagonal lattices, where at high temperatures above the Nernst transition, develop an hexagonal diffuse signal, right? And this is a consequence of the strong magnetic frustration. So in the same way, this the hexagonal diffuse charge scattering we have observed here is a consequence of the geometrical frustration. If we look at the half integer values of L, we do see this hexagonal shape of the diffuse signal, but the hexagon is not close. And this is a consequence of the in-plane vibration of the germanium iron atoms in the unit cell. So we can actually understand this hexagonal diffuse signal, this frustration, geometrical frustration diffuse signal, by considering a set and stacking of dimerized and undimerized clusters in the P6MM symmetry. So as I said before at the beginning of this chapter, below the charge order, the charge order transition, the trigonal germanium atoms dimerize and form pairs of dimer and non-dimer pairs along the z-axis. So we put and make a toy model stacking dimerized and undimerized clusters in a triangular lattice. I mean, there is one position, one corner of the lattice where we cannot put dimer or non-dimer, as the system is highly frustrated, right? And we can map this frustration in assuming an Ising model, an Ising Hamiltonian, where we give the isospin values of ±1 to dimerized germanium and non-dimerized germanium. Where the z-axis, I mean, this is the Ising Hamiltonian, sigma, I, sigma, j are the spin C1 and C2 are just strain parameters, which account for the coupling between the dimerized and non-dimerized germaniums. I have to say that here in this model, we only consider dimerized germaniums. We get rid of all the rest of the atoms. We don't consider iron at all. So there is no magnetism here. So if we do this and minimize the Hamiltonian, we end up with a configuration which looks something like this, right? But there are regions of the space where they are highly ordered and regions where there are less ordered. But then if we do the Fourier transform of this configuration, we can actually come out with the same diffuse pattern or the same diffraction pattern as we have experimentally observed, both in the HK and 2 plane and H0 plane. So the message I want to convey here is that unlike the scanning vanadium 16.6, where the charge order is driven by a softening of a mode, here the charge density wave, I wouldn't call it charge density wave, I call it just a periodic lattice distortion or a structural distortion, is a canonical order disorder transition like it happens in the spin glasses, for instance, right? So the last, with this I want to finish, and some results I would like to flash, which we are working on now, is the lutetium iron 6 germanium 6. The motivation for this material actually comes first from the theoretical prediction of or theoretical description of these Kagome materials based on this Lego-like building block by Andrea and Claudia Felser. So we wanted to demonstrate that this Kagome picture actually works in the 166 materials. And the second motivation for this work, actually, I am always following up what you guys do here at RISE, is this paper recently published in PRL a few months ago, I think, where the group of Pen Cheng measured the anomalous Hall effect in the ytterbium iron 6 germanium 6 sample. So this, I tried to measure the ytterbium sample. Didn't click, so it was a kind of a rock, but we come up with the lutetium one, which actually is has the same structure. Double layer Kagome plane is like in the scanning vanadium 16.6. It has an antiferromagnetic transition around 270 Kelvin, but and the spin configuration is the same as iron germanium. Spins are out of plane. It's the A-type antiferromagnetic material. If we look at the phonon spectrum, all phonons are positive. We don't expect any charge order, any charge density wave, or any new periodic lattice distortion, which indeed we confirmed by the diffuse scattering experiments. At high and low temperature, the diffraction pattern is more or less the same. Sample is good. As you can see, bracts are pretty sharp, despite this is a diffuse signal. And then if we look at the ARPES spectrum, here I plot the Fermi map, the Fermi surface map, which actually looks, I mean, it's hexagonal, which is a bit different as the iron germanium, but still we have a hexagonal Fermi surface with pockets at the K position and some electron pocket here. The compound is essentially two-dimensional. We don't see any dispersion or barely any dispersion of the bands. Perhaps this is disperses a bit, but it's merely a two-dimensional Fermi surface. If we look at the band, valence band, we can distinguish the Van Hoek singularities at M, some Dirac crossings at K. Bands are really a bit broader than the compared with iron germanium. And we do the DFT calculations. We, as of now, we don't have a perfect matching because these are essentially bulk calculations, and we didn't consider the surface terminations. In any case, we are working on this. It is not a high priority now because what I want to show you is that when we do the cut along the KMK direction, which is this cut here, we see how at M point, a waterfall of intensity which emanates from the Van Hoek singularity. And this waterfall of intensity is actually very well reported in strongly correlated materials, like in cuprates, and more recently, nickelates, and I think this is the heavy Fermi compound lithium vanadium 2 oxide further recent paper by archive paper by the Kagome. So this is a waterfall of intensity, which is a hallmark of strong correlations in the energy spectrum. I mean, there is still a strong controversy about that. It might be driven by the coupling to bosonic modes, hidden fermions, multi-orbital physics, and so on and so forth. We are not pretty sure where this comes from, but we made a first preliminary analysis. Actually, this is not first. We have a second analysis of this, which I got yesterday or 2 days ago, which is more advanced. In any case, we can actually model, start to model this waterfall of intensity following the two-plate bibliography by renormalizing the bare bond by the real part of the electronic self-energy. So essentially, this waterfall of intensity, which we get here, is a consequence of the split off of the Hubble band from the quasi-particle peak. Right. In any case, the message I want to convey here, hopefully soon there will be a manuscript where we will report all of this. The message I want to convey here is this 166 iron lutetium iron compound. This actually has a strong correlations in the energy spectrum, which is something we didn't see in the iron generating spectrum. Yeah, and with this, I would like to finish with the conclusions. I showed you some data which demonstrates a soft mode in the standard vanadium 6 and the charge order or periodic lattice distortions in the iron germanium given by the order disorder, transformations and signatures of the correlated Kagome metal in the lutetium iron 6. Thank you.
Can I ask? For the Lutein, for the last part, do you see, if you look at the EDCs, is it continuous or do you see like a dip central energy scale?
Here.
Yeah. Because in the Cooper example, there's like a sharper dispersion, like sharper particles above. Yeah.
Well, we didn't measure below 1 electron volt. So
Okay.
we don't see at the end of the waterfall.
Okay. But I mean, like if you were to take an EDC, you can see the sharp peak.
Yeah, here.
Yeah, and then separated by like this waterfall.
Well, we are working on that. That's the thing. I mean, the problem is there are multi bands there, a lot of bands. So we need to know which band to subtract to get that. So this is actually very complex and elaborate data processing, and we are working on that. So the Lim, the program is working very hard on doing this. So we are. I mean, it's not so easy to get. I mean, here there are many bands. So actually, we need to first understand very well and match all of these ARPES and DFT to then subtract bands here and get to that. It is moving slowly. We got this data like a year ago. We are still trying it.
It's very interesting. Any questions?
Does this waterfall feature have a photon energy dependence?
I don't think so. It's actually it appears in the whole region of photon energies we measure here. So it's not coming from the matrix elements or photon energy dependence. So it's actually solid. Now this is solid expressed in something. So with this, indeed, I mean, I have to say, because I was catching up with the literature in the cuprates, there are actually reports which are right now is people believe, and it's quite solid, that this waterfall is inherent to cuprates. But at the beginning, like 20 years ago or something like that, when people started to report this waterfall, there are reports saying that this is a consequence of the matrix elements in ARPES. I think now this waterfall is solid, something which it seems that we doesn't agree.
I haven't kept up with this part of the picture.
Yeah, but it appears in the cuprates and also nickelates, and now in this Californian lithium vanadium.
Do we know the Sommerfeld coefficient for this compound?
Not yet. And we actually the transport data which we measured, we didn't see any anomalous effect with the field perpendicular to the plane.
Okay.
But we have to measure in plane, which is what you guys measure in the interval, right? In the interval, the anomalous effect happens to be with
Yeah. Yeah. Any other questions?
You don't have it in terms of the magnetism of this one?
In the 1666,
This one.
and this one is antiferromagnetic like iron germanium. Transition temperature is 270, 280. Yeah. So this is magnetism, and perhaps it has also some conical real spin reorientation below 50 Kelvin, like all of the 70 units. So yeah.
The iron germanium part, I'm gonna follow, what's the reason of neglecting the iron atom? Is it on the phone?
Is essentially just minimizing the model so we can make it easy. That's all. So I mean, all the physics, all the important physics happens in this polarization. So we wanted to keep the minimum model to explain that. There is a follow-up of that paper, not in iron germanium. I show you, which I didn't mention. It is this one, ytterbium. 1/2 cobalt 3 germanium 3, where we actually see again this hexagonal shape of the diffuse signal. But in this case, I mean, you can see how the diffuse is again anisotropic, right? I mean, here is isotropic, but if you move out in momentum, the hexagon doesn't close, right? I mean, this compound is the way same 166. It is written 1/233 because there is some twisting and disorder there. Ytterbium occupies some of these germanium pairs. But anyway, what really matters is that we can actually model the diffuse scattering, you see, with the anisotropic hexagonal shape, considering all the atoms in the unit cell. In this case, we do not only have these germanium pairs in the Hamiltonian, but also consider out of in plane displacement of ytterbium atoms towards the hexagonal germanium and the hexagonal honeycomb germanium towards the trigonal germanium. So if you consider all of this, we model this in with the Hamiltonian, including this Lennard-Jones potential, we can actually come up with the perfect description of the diffuse scattering. The paper is accepted, will be published likely this week. So if you want to look at it. But we did that.
Was this also the Monte Carlo simulation? Or
Yeah, it's Monte Carlo.
I see.
So this is, I mean, this is the diffuse scattering without considering only germanium pairs, right? You see how the diffuse is symmetric, excellent. But if you consider this and you take into account how the ytterbiums and the hexagonal, the honeycomb germaniums move in plane, you can actually perfectly model the hexagonal diffuse scattering like we get here.
Any other questions? No, so thanks, Santi, very much.